Today we are going to be discuss about the linear motion and the rotational motion. Basically, we are going to be discuss about the differences between them, and it will be useful to the student that are looking for the revision of the rotational dynamics and how the linear motion, the variable of the linear motion and the rotational motion variables are related to each other. This is the main purpose of this video is. So it can help to the AP board students, A level student, and the IB student if they have the HL level. So it can help those type of the students. So this is in linear motion and the rotational motion, the differences between them that we are going to be looking into that. So linear motion, if I had to mention, there is a center of the mass of the body. So this is the center of the mass of a body that get moved from one position to another position. This is we call it a translational motion. So this is, let's suppose it get moved from this position to this position. So its center of the mass get moved. So in this one, none of the particle we are talking about, it have the any kind of the rotation of the things are. So it is just, you can think like this one, this remote control has moved from this position to this position. Eventually, it haven't rotated. Any kind of the rotation doesn't happen. So right now, then we have the rotation motion. In the rotation motion, the object is going to be rotate about some axis. This is a pure rotation because its center of the mass is not moving. This is another situation. So this is some kind of the linear motion we have it. This is the example of linear motion. The car is moving on the road and something. This is the linear motion that we study eventually before going to the rotational motion. Then we have the pure rolling motion. In the pure rolling motion, we have some kind of the disc or any other thing. The wheel is rolling about a pivot point. So this is rolling. So this is, if it is, this is the pivot point about which it is rotating. This is a pure rotation. Pure rotation. It is a pure rotation example. Then we have the example of the rotation as well as a linear motion. So let's suppose it is something is rotating also and something is moving. So its center of the mass is moving also, and about which the other particle are rotating. So this is the example for the rotation motion. So here we have the both the motion. So if you see the center of the mass that is moving, let's suppose moving with the v velocity. This is moving with the v velocity. This is the center of the mass get moved. So this is some kind of the linear motion that I'm going to talk it. And now because each of the particle is rotating about this center of the mass, so some kind of the rotation parameters also we are going to be talking about here. So in our syllabus we have the basically non-slipping cases. So this is a pure rolling basically, pure rolling. So it is not going to be slip. So the when it is going to be roll, it is not going to be slip. Just like, so it is the case. So you can think like this is the lens, and it is rolling like this. It is rolling. It is not sleeping like this. So it is, we have the rolling, pure rolling motion. So that we have it. Okay. So this is both linear motion. It have the both linear motion as well as and rotation motion. This is, so let's discuss about the differences between the variables, linear variable and the rotation variables. So x is the linear displacement we have it. So when the object get moved from one position to this is the linear displacement. And here in the rotational dynamics, we have angular displacement. Let's suppose this is the, when any particle is rotating about any of the in the rotation. So this is the particle, it get moved from this position to this position, basically first particle and second particle. This angle, this is we call it a angular displacement. The angle is changing. Remember it, we take always the angle in this whole chapter of the rotational dynamics is in the radian. So we are going to be taking the radian. So if I had to tell you the relation, 180 degree is pi radian. So make sure that you always take the angle into the radian only. So this is the particle. This is, we call it a r, the radius of the particle that is rotating about this pivot point. and this is we call it a linear displacement, that the particle is changing, this angle is changing, so this is angular displacement, so this is theta. So in the rotational dynamics, we talked about how much the angle get changed. So if this is the remote control, so if I move this one, if I rotate this one, so I'm going to talk it how much angle get changed with the time. So how much the angle get changed. So this is the rotational variable that we have it. So here x, we have it linear displacement, we have here angular displacement. Angular displacement theta. And the what is the relationship between them is? Relationship between them is x is equal to r theta. X is equal to r theta. This is angular displacement that we have. Then we have the linear velocity. Linear velocity is defined as, in the known calculus we define it, rate of change of displacement. Now in the calculus point of view, I'm going to define it dx by dt. Rate of the change of the displacement over time. And now we have the here the same variable, we have omega. This is we call it a angular velocity. We have omega. So omega is rate of change of angle. So here omega, if I omega, here we have linear displacement. Here we have angular rate of change of angular displacement, means how fastly the theta is changing. So if you on your fans fast, initially it move very slowly, and the angle you can imagine in your mind, the angle is changing. As it will speed up, so the angle is changing more fastly. So the omega, we talked about how much the faster the omega is changing. So this is angular velocity that we talked about that. Now we have the, in the calculus we write it d theta by dt. D theta by dt. And what is the relation between linear velocity and angular velocity is? Linear velocity and angular velocity. Linear velocity is equal to r omega. This is the relationship. Now we have the alpha. This is, I'm going to talk about tangential acceleration right now. So if I do actually recap, we have the two type of the acceleration in the rotational dynamics. So let's suppose this is circular path. The one particle is moving. So let's suppose this particle is moving. So it has the two type of acceleration. One is along the tangent. This is we call it a tangential acceleration. I'm writing complete so that you can understand. This is a tangential acceleration. One is we have along the radius, that you most probably you studied in the centripetal force that act toward the center due to the centripetal acceleration. This is we call it a centripetal. I'm writing AC, C for centripetal acceleration, so that you can understand. So and so the resultant, they are always 90-degree to each other, because this is along the tangent line. So this is a tangent line. So along that tangent line, this is centripetal. So the resultant is acting, uh, this is the resultant acceleration. So if this is the resultant acceleration, if somebody asks you what is the resultant acceleration, if the two vectors are 90-degree to each other, so I'm going to write it like this: Pythagoras theorem. I'm going to apply the Pythagoras theorem. This is tangential acceleration. So the acceleration is come out to be the centripetal acceleration square. Pythagoras theorem, simple. So this is tangential acceleration square, and you can plug in the values, and we will come to that point. What are the values? So this is tangential acceleration. We define it in the linear kinematics, that we define it as a rate of the change of the velocity dv by dt in the known calculus case. In the calculus case, I'm going to define it, a tangential acceleration is dv by dt, derivative of the velocity function with respect to the time that we have it. Now we have the angular velocity. So this is tangential acceleration. Now we had in the same way we had the angular acceleration. So angular acceleration that we have it, that is rate of the change of angular velocity. Good. So this is the rate of the change of the angular velocity with respect to the time. In the calculus, I'm going to write it. This is alpha variable, by the way. So the alpha is angular acceleration, that is defined is rate of change of angle, this omega. So if I had to be right in the calculus, let me write it d omega by dt. And what is the relationship between that? Tangential and angular acceleration. Tangential acceleration is equal to r alpha. Just see how symmetric the things are. Just to change the any angular variable to the linear variable, you have to just multiply with this r. Just look this how symmetric the things are. You can just multiply with the r to get that angular stuff. So you can remember like this. So it is easy for to memorize. So this is how you have to write it. You can write the bunch of things more over there. So then we have the role played by the mass here. The role played by the mass here, the same role is played by the mass here in this one. So here the same role is played by the moment of inertia. Moment of inertia. And moment of inertia is I variable that we write it. So how they are related? So the moment of inertia, just like mass is some kind of the inertia. It will tell how difficult to move a something or how difficult to stop something. It is some kind of the inertia that is inbuilt into that the property. So it will tell if the more mass, more difficult. You can think like this. This remote control do not have that much mass, so I can move it easily. So if I'm going to move my table, I have to apply the more force because it had a more inertia, more mass, more inertia. But in the rotational dynamics, it is slightly different. So how we are going to figure out something how difficult or how easy to rotate or to spin, or how easy to, if something is rotating already, how to easy to stop that one. So for this one, so we have the movement of inertia. That also the same role played by the mass in the linear. Here we have the moment of inertia. To find out the moment of inertia, even I have made a short video on that one. So the relationship between them is moment of inertia is equal to m r square. This is how for a single particle I'm going to write it. M is the mass of the particle and the r is the distance at what r is the distance it is. This is a due to the single particle because the system, if it is made up of the multiple the particle, if they are discrete masses, I'm going to write like this m1 r1 square, m2 r2 square, and I'm going to sum. In if the mass is distributed uniformly and some kind of the linear mass density is given in the calculus point of view, I'm telling. So then we have the integration. This is the integration of r square dm. This is the dm is the small element of the mass we take it, but this is the separate lecture. We can plan it for this one, but this is just a, I'm trying to relate the relation here. So this is the thing that we have it. And one more thing. So this is the tangential acceleration, radial acceleration. Now the tangential acceleration we already written. This is tangential acceleration is r alpha, but the centripetal acceleration is v square by r, and v is equal to r omega. We just seen it. So I'm going to plug in the value. So r omega square by r. So r get cancel out, r omega square. So basically this is the centripetal acceleration. I mean to say that you have to write it here. Plus tangential acceleration is r alpha. So this is r is the same. So do not get confused with the small r and the bigger r if I change that one. So this is the acceleration that we have it. This is the, it have the tangential acceleration. We have the centripetal acceleration. So this is how the things are going to be work. Next linear variable that we are going to be discuss about, that is that we have it is, that is force. So the force. Here the force is in the rotational dynamics, we have the torque. This is T. And the symbol is the tau that we use it for this one. Force is just is nothing but the force is a relationship between the force. Force is equal to mass time acceleration. This is the relation, that is the Newton second law that we have it. Or the force can be written as a rate of change of linear momentum with respect to the time. Correct. So in the same way, the torque can be written as, just we have discussed, the mass can be replaced by the angular moment of inertia. So I'm going to write it, moment of inertia, acceleration, linear acceleration is replaced by the angular acceleration. So this is alpha. And the torque, I'm going to write it, the torque is equal to I alpha. And the torque, net torque, this is the net torque, this is the net force. If you remember that, the net force that we calculated always, this is the force that is the depend upon the rate of the change of linear momentum. P is the linear momentum that we have it. P is equal to mass time velocity. So that is a vector quantity. This is also a vector quantity. Force is a vector quantity. So I'm putting the arrows on that vector quantity because, so these are also vector quantities that we have. So the point is, in the same way that we have the torque, torque can be defined as, this is linear momentum. Here we have angular momentum. Angular momentum is written with the L, rate of the change of angular motion. So the L is nothing but, here mass again get replaced by the moment of the inertia. So that is I. V is replaced by the angular velocity. So this is I omega. And what is the relationship between the force and the torque? So the force or the torque that we calculated, that is the R perpendicular into F force, is equal to, even I make a short video for that also. So this is R F perpendicular, that is the case that we have it, and is equal to, so these are the perpendicular values that we have it. So R F sine theta. And if you know the cross product, it will be the great thing. So I can write it as a cross product of this one, R cross F. This is how actually we write that one. You can find out the direction of the torque also by applying the right hand rule to apply to get the direction for this one. In the cross product also, if you are aware of that one, the cross product, how to find out the cross product. So if I quickly recall that one, so if you have the A cross B vector, cross product of the vectors, it is not useful for all the students. I, J, K, that is the X component of the A, J component, K component. This is the BX, BY, BJ. So how you can find out the cross product is, the cross product can be easily we find out by this one. I'm just this multiply this one and minus this one. So if you already done the vectors, then only it is useful. Just please check it out from your syllabus first. This is the I component minus, you have to multiply these two now, minus this one. This is the J component. And for the K component, this is the K component. This is how actually we find it out that when the cross product in the quantities are. Just right now, we define the force or the on an average, the force going to be act that is depend upon the rate of the change of the linear momentum. So how much the momentum, the linear momentum rate of the change of that one. So if external force that the force is acting zero, so there is no external force. So I'm going to say change in the rate of the change of the momentum is zero. So it means the change in the momentum is zero. Change in the momentum is zero means momentum initially, whatever that is, equal to the initial and the final momentum have to be same because the change in the momentum is zero. Not I'm not saying momentum is zero. Remember it. This is a change in the momentum is zero. When this is going to be happen, this is when the external force is zero. That is on the system. External force is not acting. Then the linear momentum is uh, conserved basically. So if you remember that the momentum after the collision before the collision have to be remain the same. So this is momentum after collision, whatever that the after collision the momentum is have to be equal to the momentum before the collision. They have to be remain the same. So this is the thing that we have to take care. Now what we have it, we have the basically conservation of the angular momentum. When the angular momentum is conserved, linear momentum is conserved when the external force is zero. So here in the same way, the net, if we find out the torque is equal to rate of change of angular momentum. If net torque or the torque, external torque that is acting on the any of the system that is zero, Newton meter is the unit for that. If it is zero, I'm going to say change in the angular momentum is zero. So change in angular momentum means final angular momentum is equal to initial angular momentum. Final angular momentum is moment of the inertia. Um, final omega final is equal to I initial omega. Angular moment of inertia, initial angular velocity. So this is I omega. I omega is the angular velocity. So this is how we define that one. So this is angular momentum. Linear momentum is mv. Angular momentum is I omega because the mass get replaced with I, v is replaced with the omega. So it's everything is symmetric. If you see it carefully, everything is symmetric. So if it is uh, here net force is zero, external force is zero, it means that the momentum, linear momentum have to be conserved. If net torque is zero, the angular momentum have to be conserved. So this is the relation that we have it. So hopefully till now you understood this one. The net force is equal to mass time acceleration here. Net torque is equal to moment of inertia into alpha. In the we had the work done now. What is the work done here is how we calculate the work done. Force into the linear displacement that we have it. Here we have the same thing. So work done, I'm going to calculate like this net torque and the change in the theta, how much the angular displacement is changing. In the calculus point of view, I'm going to write it here. The work done is integral of f dx. So if the force is changing with respect to the displacement as the displacement is happening. So here we have the net work done is equal to torque, how much the torque is, how much the torque with respect to the theta is changing and d theta. This is the net work done that we have it. And one more thing that I had to be recall. that here, so here, in the calculus point of view, you can write it the net torque is equal to dl by dt. If I had to find out the change in the linear, you can take it that dl is equal to torque with respect to the time that is changing dt. This is only for calculus point. So this is the change in angular momentum is nothing but the integration of d torque dt. This is, we call it a angular impulse. In the same way, we have the concept of linear impulse. So if I talked about the linear impulse, because the force is equal to dp by dt, this is calculus point of view I'm writing. So without calculus, I have to write d delta by this one. So this is the change in the momentum is equal to force into delta t. This is, we call it impulse. So that impulse, if it is in the integration, I'm going to calculate the change in the momentum or change in the linear momentum is integration of force as the force is changing. This is into dt. This is, we call it a impulse. This is, we call it a impulse that way. If I have to some more things, I have to add this one. If it is the time here, if it is the force here, the area under the curve will give you the impulse. Impulse is nothing but change in momentum. Impulse. This is the change in the momentum that we have it. In the same way, we can find out this one also. So we have the integration. In the linear motion, we had the linear kinetic energy. So the kinetic energy, we write it like this: half mv square. Here we have the rotational kinetic energy. Rotational kinetic energy is equal to the half I omega square. This is for pure rotation that we have. The power can be written as F into velocity. Here we write it the power as a torque into omega. Torque into omega, the power is. The impulse that we already did. So the impulse is force into delta t. Here we can write it angular impulse. Angular impulse can be written as torque into delta t. So these are the things that you had to be keep in the mind. So please, if you want to, this is the thing, these are the bunch of the variables that we have it. Thank you. If you want to take the screenshot. Hopefully you like it. Any of the things is still pending, you think it so please comment in below and I will try to reply and I will try to make the videos on that one also. Thank you.